All right, so let's get started. Today I would like to move towards three-dimensional wave functions, three-dimensional quantum physics. But before I'm able to do that, just a quick recap of the time-independent Schrodinger equation in 1D. So we have this term minus h bar square over 2m. Then the second derivative of the wave function in space. This term corresponds, as we know, to the kinetic energy plus a potential energy term, and all of this equals the energy of the particle. This is the time-independent Schrodinger equation, and we've solved this equation for number one, the infinite well, and we've also seen what happens when the object encounters a potential step, and we've also seen when the object encounters a potential barrier. In this case, quantum mechanical tunneling is possible. So an infinite well looks like this. The potential energy goes to infinity outside the box. A potential step is a change in the potential energy, either positive or a downward pointing step. Both of these qualify as potential steps. A potential barrier is that when an object sees an obstruction and then the obstruction finishes and the original potential energy is recovered. We've seen in all of these cases that reflection and transmission at boundaries can take place, and in each case you have to satisfy the continuity of the wave function and the continuity of the first derivative of the wave function. So all of this is what we've done so far. We've also seen how to calculate potential energy given a potential energy landscape. How do we, for example, calculate or sketch or estimate wave functions? So if this is the fixed energy of a system E inside this potential energy landscape, when all of this goes to infinity and there's a hump over here, given some quantum state, the wave function will act in such a way that in this region the kinetic energy is going to drop. Here the kinetic energy is high. Kinetic energy high means the k value is high, which means that the wave is shorter, the wavelength is shorter. So you'll have a scenario like this. All of a sudden here the wave function expands, it dilates and also grows bigger in size. It grows bigger in size because the particle is slower here. So if it's slower here, you take the modulus square of this wave function, you get bigger probabilities in this region. Wherever the particle is slower, the wave function goes up in size and up in amplitude. The wave length, which is the inverse of the wave number, shows the kinetic energy. And the kinetic energy is basically the difference between the energy, which is this much, and the potential energy in this region. Here this gap is large, which means that the kinetic energy is large. Here the gap is small, the kinetic energy is small. This is so far what we've done. So I just wanted a quick recap because now we're talking about quantum physics after almost a week. This is our time-independent Schrodinger equation, and the key idea is that you need to find the potential energy landscape. You plug that potential energy landscape into the equation, and then you get a differential equation and you solve it to get the wave function. You get the wave function, you get the probabilities. So that will tell you where the particle is likely to be found. Now another example of a wave function is which is very useful is the idea of the harmonic oscillator. Now suppose I have, let's look a little bit at classical physics. Suppose I have a mass m, it's an object that lies on a frictionless surface and it's connected with a spring to a support. This is an oscillator, this oscillates and will have a certain natural frequency. So what is the natural frequency of this object given the mass and the spring constant? What's the natural frequency of this object? Every pendulum has a natural frequency that depends upon its length. So what's the natural frequency of this oscillator? It's k over m under root, or omega square is k over m. So omega is the natural frequency. Now what is the potential energy of this object? If I were to take an equilibrium position and distance from the equilibrium position is x, what's the potential energy of this spring plus mass system? Half kx square. So the potential energy is half kx square. Got it? Now suppose this were a quantum particle. It wasn't a mass, it wasn't a macroscopic big object, rather it was some quantum particle. For example, I have a nitrogen molecule. And when I talk about a nitrogen molecule, basically two nitrogen atoms are bonded together. So I have a nitrogen atom and another nitrogen atom, and there is a covalent bond between these atoms. Now that covalent bond binds these nitrogen nuclei together. Now I can model this. I can model this bond as a spring that connects the two nitrogen atoms. Because as you know that this atom is also vibrating. So this molecule on a whole has different degrees of freedom. If you put nitrogen in a cylinder, so 1 degree of freedom is that the molecule translates. It can translate along x, y or z. It's moving at, shooting at very high speeds given by the Boltzmann relationship. But this molecule can also vibrate, correct? And the higher the temperature, the higher will be its vibrational energy. It can also rotate. So there are multiple degrees of freedom possible for this molecule as a whole. It can translate, it can vibrate, it can rotate. So if you just consider the vibration of this molecule, the vibration is akin, or it can be modeled by a spring that connects the two nitrogen atoms. All right. So now this is a truly quantum mechanical system. It's not a big object. It's small nitrogen nucleus, 7 protons, probably 8 neutrons. That's it, and a bunch of electrons, 7 electrons around a single nitrogen nucleus. So this is a small molecule. Now its vibration has a certain energy, and that energy is given by this thing. So given some equilibrium position, if this molecule were to vibrate, compress or dilate, its energy is going to go up. So the molecule has a certain energy, potential energy associated with it. If I were to make a graph between the distance between the two nuclei and the potential energy, can you, yes please? नहीं bonds तो fix होते हैं, लेकिन वो bonds की जो length है वो change होती रहती है. Bond length एक equilibrium bond length होती है. This is an equilibrium bond length, but the bond can compress and expand. So the temperature goes up, the vibration goes up, which means the amplitude of vibration goes up. That's what temperature really means. So when temperature of a molecule goes up, it can translate with higher speeds. The speeds are given by a Maxwell-Boltzmann distribution, but it can also vibrate with higher speeds. It can also rotate with higher speeds, because any energy that goes in is distributed in all the degrees of freedom. This is called the principle of equipartition of energy, and it's equally distributed in all equivalent degrees of freedom. So the bond is there, but it's vibrating. So if I were to plot a graph between the potential energy of this molecule and the distance between the nuclei, can you guess what this graph is going to look like? So what if the molecule, if the atoms get closer, the energy goes down, because only then will a bond be formed. So when the atoms are far apart, there is no potential energy. The two nuclei are free. They are uninfluenced by one another, so the potential energy is 0. But as the molecules get closer and closer, the potential energy drops. But if they get too close, the potential energy goes up. So the nitrogen nuclei cannot get too close to one another because of these electrostatic repulsion effects. So at one point, this curve takes a turn and goes back up again. This point at which this energy, the potential energy of this molecule is minimum, that's generally called the bond length, R0. So every molecule has a bond length. It's a diatomic molecule, it has a bond length. So there's a potential energy curve associated with this molecule. You had a question, my friend?
Yeah. This possibly would only be true for non-metals, right?
For
Non-metals.
Yeah, non-metals, so metals do not form bonds like this anyway. Metallic bonding is different. So this is a covalent bond, it's a diatomic molecule. So this is the potential energy distribution. So now probably we can solve the potential energy, given the potential energy landscape, we can put the expression for this potential energy into this equation and solve what the wave functions for the vibrational degree of freedom for this molecule looks like. But it appears that this is a really complex function. It doesn't have a nice straight line, it's not like an exponential, it's slightly more complex. If I were to take this potential energy distribution, Vx, let me plot this. Say, instead of x, I use r, Vr. So what does that curve look like? What does this look like? It's a parabola, right? It's a parabola, it looks like this. So this is some half k r square. All right. Now if you have such a potential energy landscape and you put this equation, this expression into the time independent Schrodinger equation, what do you have? You have minus h bar square 2m d square psi x dx square plus half kx square psi x. I'm using x again, e psi x. Now a new differential equation is formed. You solve this differential equation, you get the wave functions. Now solving this differential equation is slightly more complicated. You can look up any textbook on quantum mechanics to solve it. I will not do it for you because it's slightly involved and it's long. It's going to take up all the time that I have in front of me. So you solve this equation and you get what are called Hermite polynomials. And you also get a quantum number n. You get a quantum number n, and that defines the wave functions. So you get Hermite polynomial. So the solution to this, the lowest order solution is psi 1, quantum number n. Just to give you an example, it's proportional to E minus x square over 2b square, where b is a constant given by the value of k, but this is what it looks like. This is a wave function, and higher order wave functions also exist, just like an infinite well. In an infinite well, you might remember that there's a low energy solution E1 and a wave function associated with it. This is n equals 1. Then you have a higher energy n equals 2 wave function and an energy associated with it. So the energy is quantized, and with each level you get a new wave function, and these wave functions are identified by a quantum number n. Exactly the same thing happens here. It's just that the wave functions are not sine waves. They look like sine waves, but they're not. And the nice thing is that the energy gets quantized as well. Now in an infinite well, what does the energy landscape look like? What are the quantized energy levels looking like in an infinite well? What do they look like? Are they equally spaced, or? So they increase quadratically. The nth level is n square energy of the ground level. So the energy levels, they're not equally spaced, they go up quadratically in an infinite well. But if you solve the harmonic oscillator, all the energy levels are equally spaced. All right, all the energy levels get equally spaced. So this is a hallmark of a parabolic potential energy curve. This is called a harmonic oscillator. So the energy levels in a harmonic oscillator, they are equally spaced. Equally spaced. And the nice thing, so the lowest level is n equals 1 level. This is the n equals 2 level, and there's a quantum number associated with these levels. And the nice thing is you can come up, it's evident that when you solve this equation that these energies are quantized, and the energy is given by a simple formula that you need to remember. The energy of the nth level is given by n minus 1/2 h bar omega, where n, it can be 1, lowest energy level, 2, 3, and so on. So the energy is quantized, and the lowest energy level will have an energy. This energy is going to be h bar omega over 2. The 0 point energy for the harmonic oscillator is half of h bar omega, and this omega is given by k, square root of k over m, and for the bond there is some effective bond strength which can be written in terms of k over m. So this is the lowest energy level. The next energy level would be 3 times h bar omega over 2. The next one would be 5 h bar omega over 2. And the gap between two successive levels is always h bar omega. So if I were to plot this again in a zoomed in fashion, this is my potential energy landscape. So this is an energy diagram. This is my potential energy. Vx is half kx square the energies are quantized, equally spaced. H bar omega over 2, 3 h bar omega over 2, and so on. This is n h bar omega over 2. The 0 point energy is still not 0. So you have an harmonic oscillator, you cool it down to 0 Kelvin, it's still not going to cease its motion. It's always going to oscillate, going to jostle around. Even vacuum has this much energy. So there is no such thing as nothing, as I mentioned earlier. The gap between any two levels is h bar omega. So if an electron or some system were in this state, which corresponds to n1, 2, 3, 4, so this is the n equals 4 state, the energy would be 7 h bar omega over 2. And if that system makes a transition, falls down to a lower energy state, it emits a photon, it emits light. That light will have a certain frequency, certain wavelength, and a certain color. Arbitrary colors, arbitrary wavelengths cannot be emitted. So this gap is now 7 minus 3, which is 4 h bar over 2 is 2 h bar omega. So this photon will have an energy 2 h bar omega. And from this you can find out the frequency 2hf. You can find the frequency of this photon. And you can find the wavelength of this photon 2hc over lambda, where lambda is the wavelength of the photon, and from the wavelength you can tell the color of the photon. It might lie, by the way, in the ultraviolet or X-ray or any other regime, microwave, infrared. That depends upon how big this gap is. So when you have a harmonic oscillator of this kind, which has an energy structure of this kind, when you see light from this harmonic oscillator and you look at the spectrum of that light, you can tell what the energy levels look like. This process is called spectroscopy. And by the way, the wave functions, so if I were to draw, let me just draw the basic wave function, the n equals 1 wave function, and then I'll take a question. So this is the energy E. The basic wave function is this thing. That's the lowest energy wave function, the ground state wave function. If I were to plot this, so if I were to plot this, so suppose I plot it over here. This is my wave, this is now my wave function axis, the 0 for my wave function axis. So this is a decaying exponential with an x square term. So it looks like this. It's not a sine wave, but resembles, it's like a decaying exponential but with an x square. Okay, this is a plot of psi 1x with n equals 1. This is some constant. Normalization can give you this constant minus x square over 2b square. Now question, this yellow shows my wave function for the ground state. In this regime, yellow shows my energy and pink shows my potential energy. In the regime, so let's call these points, let's call this point B, let's call this point minus B. Okay, so this is a position axis. Now for x less than or equal to B and greater than or equal to minus B, what can we say about the kinetic energy of the system? Positive or negative?
Positive.
Positive, because the energy is bigger than the potential energy. So the wave function has some oscillatory behavior. Not really, but the wave function kind of shows this pattern. Now beyond these points, when x goes beyond B or x is less than minus B, so you go beyond this point. At this point, the energy of the system, which is this line, becomes smaller than the potential energy, right? So the kinetic energy technically becomes negative. Now, how does quantum physics deal with these problems? It deals with these problems by telling us that the wave function simply dissipates, goes down to zero, but it does not immediately go to zero because it's not an infinite well. Remember our discussion on the potential well? The wave function does not immediately go down to zero, it just decays slowly. That's what is happening here, because the potential energy is still not infinite, it's finite. It's bigger than the energy, but still finite. So the wave function leaks out into this classically forbidden region. So beyond B, beyond this region, and here, these regions are classically forbidden, but still the wave function can leak out into these regions. Alright, so this shaded region shows us the classically forbidden region. Now the harmonic oscillator is really important in physics. Some people would say that all of physics is about the harmonic oscillator. It's all about these oscillations. You talk about a photon, the photon can be described by a harmonic oscillator. Electromagnetic fields can be described by harmonic oscillators. Even if you look at this molecule here, this is a molecular potential energy landscape. Here we're talking about the vibrational degree of freedom. In this case, can you see a harmonic oscillator hidden somewhere? This is a potential energy curve. Can you near where? Near the equilibrium point, this bowl here of the potential energy, this bowl looks like a harmonic oscillator. The potential energy landscape looks like a harmonic oscillator here. It kind of looks like a parabola. So I can draw that parabola here. So close to the equilibrium bond length, the potential energy landscape is looking like a harmonic oscillator. So if the molecule is at its equilibrium bond length and it kind of vibrates and the amplitude is small, the amplitude is not large, the amplitude is small, so that the molecule just oscillates here, here. It doesn't have large swings. If it just oscillates very close to its equilibrium point, which is generally the normal situation at reasonable temperatures, then this molecule lives in a potential energy landscape that resembles a harmonic oscillator. Got it? नहीं समझ आई क्यों? You see, this yellow curve is the potential energy curve for a molecule that wants to form a bond. In this region, if I superimpose the diagram of a harmonic oscillator in this region, the two curves almost match close to the equilibrium point, right? They deviate when you're very far away from the equilibrium point, both in this direction as well as in this direction. So very close to the equilibrium point, this yellow section of the curve can be drawn or considered to be a harmonic oscillator. Correct? Therefore, in this region, if the molecule always remains in this region during its course of vibration, you can model this vibration as an oscillator inside a harmonic potential well. Correct? Any question about this? Is that clear now? Ma'am, is it clear? Now in this region, you just apply the tools of trade that you learned from the harmonic oscillator, and the potential energy for this system, which is associated with the vibrational degree of freedom, is now harmonic in nature. So the energy levels for the vibration of this molecule, they are now quantized and they're represented by equally spaced levels. So the vibrational degree of freedom of this molecule is also quantized. The vibrational energy of this molecule is quantized. Every molecule will have vibrational quantum levels, and you can assign numbers to them. This is the n equals 1 vibrational level. This is the n equals 2 vibrational level. And in fact, you can do spectroscopy based upon these vibrational levels. Whenever there's a transition between two vibrational levels, a photon is emitted. Or if light is shown into a molecule that can vibrate. For example, I have this quantized vibrational level structure in a molecule. All of these levels exist. Now if I shine light onto this molecule, light comes in. If I were to make a plot of the frequency of light versus intensity of light. If this molecule didn't exist, and I had a detector over here, in fact a spectrometer can tell you the intensity versus the wavelength. And if this is white light means it has all the wavelengths possible, and this molecule didn't exist, what kind of spectrum would you get? What kind of spectrum would you get? All wavelengths will pass through, correct? So there will be almost equal intensity at all wavelengths, because that's the it just represents the spectrum of the incident light. So you get conceptually something like this. This is no molecule present. No molecule is there. However, now I place in the nitrogen, a cylinder with nitrogen molecules, and light passes through. This white light source is shown onto this molecule. Certain wavelengths will be absorbed. Those wavelengths correspond to these gaps. So if this molecule were in this state, it will be possible to absorb this wavelength, because this is a precise gap. This gap corresponds to a wavelength. So one wavelength will be absorbed. It's also possible that if you had another molecule in this state, in this ensemble, in this large collection of molecules, this transition could have taken place. This transition could have taken place. This transition could have taken place. If in the original system you had molecules already in the excited state, because the temperature is high, there will be some molecules in the higher state, some molecules in the lower state, and there are formulas to tell you that as well, then all of these transitions can take place, right? All in all, if now you were to plot a spectrum of the received light, what will it look like? Can I pinpoint and seek answers to you? Anyone in this row, please? आप बता सकते हो आप में से कोई? Okay, now you have this. हाँ, आप इधर उधर देख रहे हैं ना सारे, आप में से कोई बता दे कि now you shining light onto this molecule, this collection of molecules, what kind of spectrum would you expect? Any ideas? Yes, please. आप बताओ. हाँ. What will happen to them? We'll see them on spectrum. Yes, please.
Sir, the omega will change, and it will change according to the wavelength of the light that is being emitted. The intensity will depend upon the amount of light that is going in.
No, the amount of light going in inside. Now you have a spectrometer on the other side. What will the spectrometer see? Yes.
Will we see gaps?
No.
Distinct points.
Is there going to be a dip?
Dips. Where?
Or where it's absorbed back into their wavelength?
Yes, please. नहीं नीचे ऐसे से नहीं जाएगा.
There will be holes at the points.
Exactly. So the spectrum will look like this. So at certain points there will be dips. A dip here, dip here, dip here, perhaps bigger dips, smaller dips, and all of these dips. So if I take this to be h bar, if I take my axis to be h bar omega, these dips will be at 1, 2, 3, 4, 5, and so on. Because these wavelengths will be subtracted from the light, because that light will have been absorbed by this molecule. Yes, please, just a minute. So these wavelengths are now absorbed by the molecule, so they are unavailable at the spectrometer. They have been taken away by the molecule, right? So there will be gaps in the intensity, holes in the intensity, dips in the intensity at those precise wavelengths. And those wavelengths are h bar omega, 2h bar omega. This corresponds to a transition between two levels, which are spaced 2 units apart, 3 units apart, 4 units apart, and so on. So there will be dips in the spectrum. By the way, this is called vibrational, because you're looking at the vibrational degree of freedom, vibrational absorption spectroscopy. So this is an example of an absorption spectrum, and the spectrometers that can do this for you. By the way, the vibrational levels are in the infrared regime. Infrared regime. So there's an equipment that does this for you. It's called an infrared spectrometer. In fact, you might have used one in your Chem 101 lab, an instrument called a Fourier transform infrared spectrometer, FTIR. So now if you look at the spectrum, you can tell what the energy levels inside this molecule, what are the vibrational energy levels. Yes, please, you have a question. क्योंकि absorption हो रही है ना, तो intensity जो यहाँ पे आ रही है at those wavelengths is going to drop. That intensity is now not available at the spectrometer because those wavelengths have been absorbed by the molecule. And you had a question here? Yes, please. So from the peaks, from the position of the peaks, we can tell what are the gaps. That's spectroscopy. By looking at the spectrum, you can tell where is it coming from, what is the energy level structure of that molecule. Okay, so it's like a signature of the molecule. You want to identify nitrogen from oxygen, from hydrogen, from other molecules that can vibrate. You have a complex molecule like ethanol, acetone, and each of these functional groups is vibrating. They will have precise frequencies. So the infrared spectrum can tell you what are the vibration levels that exist inside this molecule. I have one question before I can take yours. Why are these dips of different heights? Yes, please. No. When all of these gaps are h bar omega, 2h bar omega, 3h bar omega, 4h bar omega, so that identifies the positions of these peaks. But why are they of, have I drawn these of different heights? Yes, please. The blue shirt, please. There are many options, yes. But you have an infinite number of levels available. Yes, please.
Does it correspond to like the number of molecules like changing with that? Like
Exactly. So it corresponds to how is this energy manifold populated in the first place. You can have many molecules in the low energy state, lesser in the high energy state, even lesser in high energy states. So if you have a distribution of energy levels inside a molecule and you want to have many molecules, all of them will not be in the ground state. There will be a distribution of levels. So if I were to draw this, you're learning a lot of quantum physics here in one go. So you have different levels. Energy E1, E2, E3. The fraction of molecules inside an energy level E, N, is proportional to E minus E raised to power minus En over kBt. Now this is a formula that should be ingrained in your minds. even if you're not physicist. Higher the energy, this thing goes up, this exponential factor goes down. So higher energy levels are less likely to be populated. Lower energy levels are more likely to be populated. This formula is called the Maxwell-Boltzmann distribution of energies, populations. So this formula tells us, so according to this formula, which of these levels will have the most population. By the way, this tells you what happens in equilibrium. In equilibrium, if everything is set up in equilibrium, everything is at the temperature capital T in kelvins. This is the distribution of populations inside an energy landscape. On the ladder of energies, this is how many people are standing on the lower rung of the ladder, how many are standing here, how many are here. So where will be the highest population? At the ground, at this level. So if I were to draw the populations just by these beads showing the number of molecules in this level, this is what it's going to look like. Here there will be fewer, yet fewer, yet fewer, and so on. That's why since these populations are different to begin with, that's why these intensities have different heights. And there are other things that you learn in atomic physics which are called selection rules. Which energy level transitions are allowed and which of them are forbidden. Yes, please.
So, if that's the case, shouldn't we expect कि जैसे wavelength ज़्यादा हो रही है, आपकी depths कम होती जा रही है?
Wavelength ज़्यादा हो रही है, frequency बिल्कुल ऐसे ही होगा. Well, you really need to look at the specifics of the system to draw this really accurately, but the point that I want to make is that these dips are of different height. Yes, please.
So for a dip at 3, for example, that means that the photon emitted has an energy of 3 h bar
Omega. And that can come in different, it means that a transition between levels that are spaced 3 units apart. This could be this transition, this transition, this transition, and so on. All of those are contributing to photons of this same wavelength.
So if that is the case, won't that only tell us the energy gaps?
It tells us the energy gaps. That is what is important.
It does not tell us the vibrational energy levels.
I mean, the vibrational energy level is the lowest energy level. You already know is h bar omega over 2. If you know some characteristics of the molecule, you can find the natural frequency, you can know what the lower energy level is. But energies are all relative. Now, let's, yes please, yes please.
The distribution, just because like lower energy has more number of particles, is it because of the entropy of the system?
It has to do with the entropy, yes. Yes, please.
Why is the peak height same for 1 and 2 and different for 3 onwards?
I mean, I've just drawn this to conceptualize. You don't take me literally for this, which peak is higher, which peak is, just showing a point here. Okay, making a point here. Yes, please. So T is the temperature, Kb is the Boltzmann constant. Yes, please.
About the variations in the curve, the graph.
This curve? So I'm just trying to make 2 points here. There are dips at precise locations. The other point I'm trying to make is that these dips are of different heights. That's it.
Why?
Because suppose because the populations are different. The populations are different. Now light is coming in. If a photon makes a transition upward, now it does not have another photon in the lower energy state to absorb a subsequent photon. However, if there are many photons available in the ground state, many transitions originating from the ground state can take place. That's why these dips are of different heights. Okay. Now let me move on. Now what I would like to kind of give you an example of is 3D quantum wave functions. And remember, here we're talking about the vibrational levels, but the rotational levels are also quantized. So if vibrational levels generally have frequencies or wavelengths in the infrared regime, you can do infrared spectroscopy to tell the vibrational levels of the molecule. In the rotational scheme, the gaps are bigger. There, the photons generally have microwave wavelengths. So you can do microwave spectroscopy for the rotational levels. Right? So rotational levels generally looked at in the microwave regime. Vibrational levels are generally looked at in the infrared regime. Electronic energy levels inside an atom, they looked at in the visible regime. I'll show you an example today. Nuclear energy levels, as mentioned in the last class, deal with photons in the gamma ray regime. Inner shell energy level transitions inside an atom emit photons in the X-ray regime. So everything is quantized. There are precise energy levels. Vibration gives you infrared. Vibration gives you infrared. Rotation, generally speaking, gives you microwave. Nuclear shell transitions give you gamma rays. Outer shell electron transitions generally give you visible, sometimes ultraviolet, sometimes infrared. Inner shell electron transitions in heavy atoms, gives you generally X-rays. Nuclear spin energy level transitions give you radio frequencies, as we dealt with in NMR. So all this is a spectrum of frequencies that quantum physics gives you. It all is coming from the energy level gaps inside the molecule, the atom, and so on. Right? So this is the entire field of spectroscopy. You want to learn spectroscopy, you want to learn how to identify molecules, you need to learn quantum physics. So quantum physics is really important. And these are really important techniques even in our daily lives. Anyway, let's move on a little bit to three-dimensional quantum physics, because we want to look at the hydrogen atom. Now, in order to motivate the hydrogen atom and what is meant by orbitals, I really want to talk about orbitals in this course, because orbitals are so important. You've been seeing orbitals from class 9 from your O levels. What is an orbital? What does it really mean? What does a p orbital mean? What does a d orbital mean? What's an s orbital? You've seen this undoubtedly in Chem 101 as well. I just want to reinforce those ideas from the quantum view. Now, if I look at 3D quantum wave functions, let me give you an example. Suppose I have a box, a cube. Now this cube, inside this cube has length L. So there's an x-axis, there's a y-axis, and there is a z-axis. It's a three-dimensional cube. The length on each axis is L. So it's a cube, right? Now inside the cube, the potential energy, say we're talking about an electron. An electron is now not trapped on a 1D well, it's trapped inside this 3D cube. It's a three-dimensional well. So the electron has been put inside the well, which is bounded by the three sides. It's like a prison cell, true prison cell. Okay. Now the electron is trapped inside, and outside the walls of this prison cell are infinite potential energies. Okay, so it's only inside this cube that the wave function can exist. Outside the potential energy landscape is infinite. So it's a 3D well, 3D infinite well. Now we would like to solve the Schrodinger equation for this. Now the wave function psi is 3-dimensional. It is a function of x, y, and z. Now let's solve the Schrodinger equation for this 3D infinite well. Do you get the point? Now, can you give me an example of how can you construct a 3D well for a single electron?
Three individual wells, like on the x-axis, then on the.
So how can you make a well for an electron? Physically, you want to have an energy where the potential energy goes infinite. How can you construct such a well for an electron? Yes, please. Exactly, you have a big plate and put lots and lots of negative charge on it. For the electron, that region is infinite potential because the electron is repelled by negative charges. So there are two large barriers on the left and the right with large negative charges, and up and bottom and front and back trapped from all sides. So an electron is in a quantum dot trapped from all sides by this huge potential barrier on all sides. Okay? Three parallel plate capacitors in one way, but both plates negatively charged. Okay? So this is an infinite well. Now if I were to write, this is my kind of time independent Schrodinger equation over here. The only thing is that now I need to deal with x, y, and z all together, and the potential energy is also a function of x, y, and z. So it's very easy to write the time independent Schrodinger equation for this 3-dimensional case. I can write minus h bar square over 2m. Take this as constant. Now I use partial derivatives. So a double derivative with respect to x followed by a double derivative with respect to y plus a double derivative with respect to z of the total wave function. Now outside the well, the potential wave function is 0. Okay, so I don't care what's outside the well. Outside the well is nothing. There is no wave function outside the well because the potential energy there is infinite. The particle cannot exist there. Inside the well it can exist. So inside the well the potential energy is 0. So I'm now writing the time independent Schrodinger equation inside the well. Inside the well the potential energy is 0. So if you look over there, top line V becomes 0 inside the well. So the right hand side, however, is E, wave function is, alright. So this is the time independent Schrodinger equation. Really simple. It's a differential equation and it's a partial differential equation. You haven't seen anything of this beast before. So how do we solve it? Yes, please. Sorry? How do we make it compact? Using? Well, this derivative, double derivative, this is already an operator. Yes, please. Well, I don't think so. Remember, how did we separate out the time dependent and the time independent part in the Schrodinger equation? Sorry? product of time part and the space part. We separated out the time part and the space part, and we proposed a solution that only had the space part and the time part and multiplied the two together and saw if that were a valid solution. This technique is called finding an ansatz. You have a trial solution and see if it works. So we do exactly the same thing. So our wave function now, remember there's no time dependence as yet. So this wave function now is separated out into an x part and a y part and a z part. Correct? A part that only depends upon small x. Let's call that part capital X. Let's call that part of the wave function capital X. Capital X, variable small x, multiplied by a wave function y that only has small y dependence, multiplied by a wave function z that only has a z dependence. Correct? This is called separation of variables. Let's propose this as an ansatz and see if it works. So now we put this thing into this equation over here. Now when I take the derivative with respect to x of the entire thing, so this term, first term, is the double derivative with respect to the entire thing. For purposes of the double derivative, can I treat y and z as a constant? Yes, okay. Likewise for the other two terms. Therefore, if I were to do that, minus h bar square over 2m, the y and the z part are treated as constants. Capital Y, capital Z is a constant function with respect to the double derivative with respect to x. However, I need to take the double derivative with respect to x of capital X. Correct? Because this depends upon x. You get this? This y depends upon y, this z depends upon small z, but I'm not going to write down these parameters over and over again. Do you get the first term? Likewise, the second term will be x z d square dy square of capital Y plus x y d square of z dz square. Correct? Yes, please. नहीं ये wave function, ये poly don't confuse these with the poly operators. These are not the poly operators. These are new functions that I'm defining, new wave functions. Okay, and this equals the energy x y z, because the wave function can be broken down into this factor. Got it? Now if I take this equation, by the way, if you notice, I've reintroduced the ordinary derivatives, because now this is only a function of x. I can do that. I mean, it's a legitimate thing to do. Now in this step, I divide this equation by x, y, z. Right? So if I do that, get minus h bar square 2m 1 over x d square x over dx square small x plus 1 over y d square y dy square plus 1 over z d square z over dz square. This is E, the energy. Got it? Now the point is, on the left hand side you have three terms. You have x dependence here, only x dependence. You have y dependence here, and you have z dependence here. So you have three terms: x dependence, y dependence, z dependence, and you add all three terms, you get a constant. Don't you?
Yes.
You get a constant. Now, what does that tell you of each of these three terms? Each one of them is a constant. Each one of them must be a constant.
Why?
Because it's not possible to have three terms, each one of them varying with respect to some variable, and you add them up and get a constant. It means each one of them is a constant. This only has an x dependence. What kind of x dependence can you think of? If there is an x dependence, this must also have an x dependence. But this is a constant. So each one of these terms is a constant. And the only reason why this is a constant, because x's and y's are not intermixed with one another. Pure x dependence, pure y dependence, and a pure z dependence are collected together, added up to give you constant. So each one of these terms must be constant. Alright. So now this is a constant, constant, constant. And those three constants must add up to give you E. Right? So let's call this constant. Let's call this constant K1. Let's call this constant K2. Or let's call it Kx, Kx, Ky, Kz. All right. Now let's look at one of these terms. Let's just look at the first term. Minus h bar square 2m d square x dx square is, I call it K1. Now if I just reshuffle this a little bit, this becomes d square x dx square plus sorry?
Wouldn't you have the x term in the denominator?
Oh, sorry. Plus excuse me. I want to call this term kx square, ky square, kz square. Okay? Two mkx square over h bar x is 0. Correct? Yes, please. क्या? So I all right. So kx square. So the whole thing is a constant kx square. Yes, please.
Whole square.
What whole square? So the first term, this term here, I call it kx square. Excuse me?
X subscript.
X is a subscript, and this constant is kx squared. Why am I calling it kx square? Because I can recognize that h bar square 2m over 1 over x, this has dimensions of wave number squared. Okay? Yes, please.
So it's including the incident factor in kx squared but not in ky or kz.
So it's the same ky square. This is included in ky square as well. Okay? Some things are taken for granted, I mean. Okay? So now this is kx squared. This is our equation. Now can you solve this? This equation can be solved. How can I solve this equation? I make an auxiliary equation. Can you please solve this for me? Can you find the solution for x? All right, let me simplify things. Excuse me, sorry. Let me simplify things. If you're not comfortable with case, let me just simplify. Excuse me. So first term, what are the dimensions of the first term? The right hand side is energy. So what are the dimensions of this term? I mean, if this right hand side is energy, so what is this term? It must be an energy, right? This must be an energy, this must be an energy, this must be energy. Alright, so let's call this Ex, let's call this Ey, let's call this Ez. Okay, got it? What's the solution to this? The auxiliary equation is q square plus 2m Ex over h bar is 0. Got it? H bar square, sorry, h bar square. What this means is q square equals minus 2m h bar square Ex. Got it? So the solutions are plus minus iota 2m Ex under root over h bar. Correct? Correct? Now let's call this thing plus minus iota kx. Now this is, as you can imagine, this is a kx. 2me square root over h bar has dimensions of the wave number. Hence the solution to this equation is x as a function of x is some constant e plus minus iota kx x. Got it? So this root goes into the exponent of e. Now isn't this similar to a one-dimensional wave function? This is exactly the same solution that we received for a one-dimensional wave function. Now can we apply boundary conditions to this? Right? What kind of boundary conditions do we apply? X at x equals 0 and x at x equals L. This must be 0. This implies that this thing, I don't want to repeat it over here, this thing is some constant sine of nx pi x over L. If these boundary conditions were to be satisfied, this must be the wave function capital X. Some quantum number nx has popped up exactly the similar manner as an infinite well, because up till this point, now we got to this point, this now looks like a 1D infinite well. The same solution would apply with a wave number kx that is now given by nx pi over L. In a 1D infinite well, I had exactly the same relationship, k equals n pi over L. So k is now quantized. When k is quantized, Ex will also be quantized, but we don't know as yet what Ex really means. So this is x in the x part of the wave function. What is the y part of the wave function? What is the y part of the wave function? Some c, let's call it c prime, sine of ny pi y over L. Exactly in a similar fashion. What is the z part of the wave function? Sine of nz pi z over L. Got it? Now we have solved the Schrodinger equation. What this means is the wave function is now given by some big constant a. I'm lumping all the constants together. Call them a. Sine of nx pi x over L, sine of ny pi y over L, sine of nz pi z over L. This is the wave, it's a three-dimensional wave function. And now you get three quantum numbers, nx, ny and nz. In 1D you have one quantum number, in 3D you have three quantum numbers. And what about the total energy? The total energy of the system is now going to be Ex plus Ey plus Ez. But what is Ex? Ex is, I've replaced Ex, this is my, Ex is h bar square over 2m kx square, correct? I'm just putting in the values from there. Ey has a ky square and Ez has a kz square. And each one of these terms is a simple substitution. Kx square is really nx pi over L. So pi square here, L square here, nx square plus ny square plus nz square. So the energy is now quantized, but now the energy is defined by three quantum variables. I'll get to you. Three quantum variables, nx, ny and nz. Where nx, ny and nz, each one of them could be 1, 2, 3 and so on. Nahi samjh aa rahi? I think this is pretty clear. What have we done? We have broken down the equation into three equations. This is what the first equation looks like. The solution to this equation looks like this. I have replaced this term with kx. Ex will now be equal to h bar square kx square over 2m. So Ex is h bar square kx square over 2m. Now where does this kx equals to this nx pi over L come from? It comes from over here, correct? Standing wave condition, 1D infinite well. Now this is the quantized energy levels of a particle trapped inside a 3D infinite well. Now what's the lowest energy state? What quantum numbers would it have? So the lowest energy state would be when the three quantum numbers, each one of them equals 1. So 1, 1, 1. The three quantum numbers, when each one of them is equal to 1 and x1 and y1, and this gives us some energy. What's the next first excited level? 211. But how many kinds of 211 can exist? There are three kinds. So there are three levels. One is 211, the other is 121, the third is 112. All three of these levels, they are different levels, but they have the same energy. Got it? So levels that are different but having the same energy, they are called degenerate levels. Likewise, you can keep on building this structure. In an infinite well, you had non-degenerate levels. They were not equally spaced apart. These are not equally spaced apart as well. Hence, a 3D infinite well is defined by three quantum numbers. The hydrogen atom is a 3D system. It's defined by three quantum numbers. What are they? They're generally called N, L, and ML. So whenever you have a three-dimensional system, you get three quantum numbers. Now I'm going to talk about the hydrogen atom in the next class, but let me show you a demonstration so that I can motivate what the hydrogen spectrum looks like. What is the hydrogen atom really? And I'm going to show you a kind of demonstration that energy levels inside atoms, and now we're talking about the electronic energy levels, they are quantized. So this tube here has hydrogen in it. This is a hydrogen tube and it has two electrodes, and I pass a high electric voltage, I give it a high electrical voltage. So this discharge takes place. When discharge takes place, it gives off different colors. It produces photons of different wavelengths. Now by looking at the spectrum of that emitted light, I can tell what the energy levels are. And first of all, I want to show you that the spectrum that you get, what does it look like? And it's kind of converse to the absorption spectrum. In absorption spectrum, you shine light and see which wavelengths go missing. Here we excite this molecule, this gas, through an electrical voltage and see that the electrons inside the energy level structure of hydrogen, they will be promoted to higher levels by fixed amounts, because the gaps are fixed, the levels are fixed. The Schrodinger equation tells us thus. But when those excited electrons fall back, they emit photons of precise wavelengths, precise colors. So let's see if we can see those colors and also look at a spectrum for this. So I put this inside this power supply. Now I also have with me an object called a spectrometer. This is a spectrometer here. This spectrometer is equipped with an optic fiber. This is an optic fiber, this thing. And I place this optic fiber close to the tube. Okay. This optic fiber will collect light that is coming out from the tube. That kind of light is called fluorescence. So the hydrogen atoms are going to fluoresce, they're going to emit light, and this light then comes out of the optical fiber. The optical fiber is a conduit for light. It takes that light into the spectrometer. This is a spectrometer. Spectrometer has a grating inside it. It separates out the wavelengths and you can plot it. So let me also kind of open my spectrometer screen here, and I need to connect my laptop too. Put in a family member's name, open the spectrometer software. So the spectrum right now is empty. Let me turn down the lights a little bit. All right, so far it's empty. This axis is the wavelength. Can I get a laser pointer, Shahid? Laser pointer. This is my wavelength. This axis is my wavelength. This axis is the intensity or the counts. This is what a spectrometer does, and this is what the spectrum looks like. In a spectrum, you have wavelength or frequency on one axis, and on this axis you have the intensity, how much light is coming in off that wavelength. So now I turn on the tube. First of all, you'll see a distinctive color to this discharge lamp, kind of pinkish, and you see two large peaks. There's a peak over here, this is a very large peak, and another peak here, and smaller peaks here. There are tiny peaks over here. So from this spectrum, you can deduce what kind of transition the atom is making inside the hydrogen molecule. Now if I look at this wavelength of this peak, this is somewhere between 600 and 700 nanometers. So I can also kind of measure the wavelength. So I put in my cursor here at the position of this wavelength. Can you note down the wavelength? The wavelength is 656 nanometers. Just note this down on your notebook. In the next lecture, we'll see whether this makes sense. 656 nanometers. Let's also note down this wavelength over here. It's about 486 nanometers. All right. So I can, in fact, there could be many more peaks inside the spectrum. If I kind of change the integration time, the peaks get bigger. All right. Now let's look at a different. Now this is an emission spectrum. Second point, it's a line spectrum. It's not a continuous spectrum. It's just precise lines over here. So this typifies that the energy levels inside this hydrogen, they are all quantized and the gaps are fixed. And when an electron makes a transition between fixed gaps, it gives radiation of a particular color and a particular kind. One more kind of light I would like to show you is something from a more complicated molecule. So hydrogen is the simplest. What's the atomic number of hydrogen? 1. How many electrons does it have? 1. Simplest system is hydrogen, just 1 electron, and 99% of the universe is hydrogen as well. The simplest system. Anything more complicated than helium perhaps cannot be solved on a blackboard or on a piece of paper. The Schrodinger equation becomes so unwieldy and the solution becomes so complex, you cannot solve it on a piece of paper, on a piece of blackboard. You need numerical simulations to solve the Schrodinger equation. This, by the way, is another gas. It's an inert gas, neon. Atomic number 10. It has 10 electrons, 10 protons as well. So let's see what happens to this. So this will have a more complicated but yet quantized energy level structure. So many photons of different wavelengths are going to come out of this. But each of these photons is going to be of a precise wavelength, indicating that even in this complicated molecule, the energy levels are quantized. So let's now replace the tube. Okay, I put this safely in a place. I load the other tube. And remember, colors tell you what the energy levels are. Colors help you identify the molecules. That's why in fireworks, when you see different colors, all of this is coming from a different molecule, from a different atom. It's coming from a different atomic level transition. So now I place this neon tube inside this power supply. The voltage, by the way, is quite high. I think it's about more than 1000 volts that is supplied to this discharge tube. By the way, J.J. Thomson did similar experiments. Rutherford did similar experiments on discharge lamps. So now let's look at, let me close this spectrometer, reopen it. And now I would like to turn this on again. First of all, you see a noticeable change in the color. It's red. Neon is red, predominantly red, around 630, 640 nanometers. This is the typical neon signs that you see on the street. And now if you look at the spectrum of this highly complicated atom, which is not complicated from a chemist perspective, but really complicated from a physicist perspective, because it has so many energy levels. It's like a jungle of peaks, a whole cornucopia of peaks, so many peaks of different sizes, different positions. The bulk of these peaks are around 600 and 700 nanometers. 630, 640 is red color, crimson red color. So that's why the discharge is of red color, because most of the peaks are in this regime. And each of these peaks, there's no lump here, lines. And by the way, each line that you see, here I've zoomed in on some lines. Each line that you see has a distinctive shape. That shape tells us the speed of the molecules inside the gas. It's not a point, it's not a Dirac delta function, it's a peak. That peak can be of a Lorentzian or a Gaussian shape. The peaks have different widths as well. The sharp peak, broad peak, that tells you the lifetime of the excited state. How long does the atom live in the excited state? If it lives longer, the peak will be sharper. This is because of the uncertainty principle. And some peaks are broad as well. So it's due to the lifetime broadening, but it's also due to the speed of the molecules. Why does the speed of the molecule give you a broad peak? Any ideas? Do you know of the Doppler effect? Some molecules are moving towards the detector, others are moving away from the detector. The ones that are moving towards the detector will appear at higher frequencies. So there is a range of frequencies present. This is called Doppler broadening. If the pressure in this tube were higher, the peaks will be broader. This is called pressure broadening. So just by looking at the spectrum, you can tell so many properties of these molecules. In fact, quantum physics was born in the 17th and the 18th century by looking at spectra of stars. And it was only the 20th century that the theory was propounded by Bohr, Heisenberg and Dirac, etc., that explained quantum mechanics truly. So energy levels are quantized. I've given you a kind of vindication here of this statement. In the next lecture, let's look at the hydrogen atom in all its glory. Thank you.